Nanoplastic as Trojan horses. Nanoplastics are plastic particles smaller than 1000 nanometer, originate as primary, manufactured, or secondary, degraded from large plastics. Their small size and large surface area make them highly reactive and persistent. This figure illustrates the sources, fragmentation process, and environmental transformation of plastic into microplastic and nanoplastic in aquatic ecosystem. Environmental presence of nanoplastic found in marine, freshwater, and terrestrial ecosystems. Enter through plastic waste degradation, industrial discharge, detected in sediments, water columns, and biota. Biological interactions of nanoplastics, easily ingested by plankton, invertebrates, and fish, cross cellular membranes and accumulate in organs, induced oxidative stress and inflammation. The Trojan horse concept, named after the Greek myth, hidden danger within a seemingly harmless object. Nanoplastics absorb environmental pollutants, carrying them into organisms, enhance the bioavailability and toxicity of co-contaminants. Physiochemical properties of nanoplastics: size, shape, surface charge, and polymer type affect behavior. High surface area allows strong adsorption of toxicants. Hydrophobicity enhances interaction with organic pollutants. Surface aging and environmental modifications. UV radiation, oxidation, and biofouling change nanoplastic surface. Modified nanoplastics show altered binding, affinity, and aggregation behavior, may increase or decrease pollutant transport efficiency. Common pollutants carried by nanoplastics: heavy metals, cadmium, mercury, lead. Persistent organic pollutants, pharmaceutical and personal care products. Mechanisms of pollutant absorption: van der Waals forces, electrostatic interaction, and hydrophobic bonding. Pollutants adsorbed onto nanoplastic surface or trapped in the polymer matrix. Complex nanoplastic contaminant aggregate from in water. Pathways of nanoplastic contaminated entry into organisms. Ingestion, the contaminated food or water. Absorption through gills in aquatic species. Cellular uptake, the endocytosis. Toxicological impact on aquatic organisms. Bioaccumulation in liver, gills, spleen. Disruption of metabolic and immune responses. Increased oxidative stress, apoptosis, and gene expression changes. Fish as bioindicators, sensitive to pollutants with measurable physiological responses, represent multiple trophic levels, indicator of ecosystem and human health risk. Uptake and distribution in fish. Nanoplastics accumulated in prime liver gonads, cross biological barriers including blood-brain barrier, detected within hours of after exposure. Co-contaminate synergism. Nanoplastics act as carriers, increasing internal pollutants dose. Combined exposure leads to amplified toxic effects, enhances reactive oxygen species generation and tissue damage. Behavior and reproductive effects alterate swimming, feeding, and predator avoidance, impaired reproduction, egg development, hatching rates, long-term effects on population sustainability, trophic transfer and biomagnification. Pollutants and nanoplastics move up the food web. Contaminants accumulate in predatory species. Potential risk to seafood safety and human health. Analytical and research challenges. Difficult to isolate and identify nanoplastics in the environment. Need for standardized detection and quantification methods. Complex mixture complicate toxicity assessment. Develop sensitive detection tools. Long-term ecosystem level studies. Conclusion. Nanoplastics act as Trojan horses, transporting pollutants, pose significant risks to aquatic organisms and humans, improved monitoring, regulation, and mitigation strategies needed.